This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to finally show you and introduce my library made for the ADS1256 AD converter. So I've been working on my custom-made circuit for a while and it works well, but I also wanted to develop my own library for this circuit. So I've been working on this for a while and I tested it with several different kind of ADS1256 circuits, including some off-the-shelf versions. But of course I also used my own circuit, and I also tested it with different kind of microcontrollers. So this is my own custom circuit. You met this in several videos. One of the most recent videos is included in the corner of the video there. But I also have some other circuits which you can buy from AliExpress, for example. But I would say that they are just now test subjects in this video, but the main focus is on this board, of course. So I designed this board, and then PCBWay made this board for me, and then I assembled it and soldered it using my own custom-made reflow hot plate as well. So it's a quite homemade stuff. And what I did is then I developed an Arduino-compatible library which makes the Arduino microcontroller communicate with any kind of ADS1256 circuit. And of course I developed all the library using this specific board, so this was continuously connected to my PC, and then I tested the code using this board. But it can work with any kind of ADS1256. I think this is the most typical that you can find if you search for it on Google, this blue circuit. But there is two versions of this blue. They are slightly different in layout. But then there is this more fancier green circuit, and there is some other versions out there as well. So they work properly with my code. And you can use it with different kind of microcontrollers. My custom board uses a ATmega32-U4 microcontroller, and I chose it because I could easily get it, and it's a chip which has a native USB, and for me that was relatively important. But you can use it with Arduino Uno or TNC 4.0 or any kind of STM32 microcontrollers. I have one of these from my earlier videos where I have the same blue board as this guy here, together with an STM32 blue pill, and it works perfectly. I also tested the code, which I will show you on this specific circuit that I'm holding now in my hand, and it works, so it's quite nice that it's compatible with everything. So what I will do in this video is that I created a very detailed handbook, a PDF file, which I will show you so you can understand how to understand the documentation. But of course you will find everything on my website, so link is in the description. Check it, please. And then I also made a demo software for Arduino, which you can load into your Arduino IDE, and then use the AD converter. So you can change the data rate, select a specific input channel, and use different kind of acquisition modes like continuous acquisition, single acquisition, and so on, and get all the data on your serial terminal. So this video will be all about the library and how to use it and how to understand it, and I explain everything. But before that, I would like to talk about the sponsor of this video, PCBWay. PCBWay is celebrating their 8th anniversary right now, so it is highly recommended to visit their website, because through their promotion they give away a lot of free coupons. They give you a huge discount on several of their services, and you can also participate in a lucky draw to try your luck and get several different kind of nice products. Alright, so first let's look at the document that I made for this library. So I decided to document everything about my circuit and about the library. So you will see everything hopefully very well explained. So there is a PDF file, and you should go to the website which I created for this library under my website. So the link is in the description, and you will find this PDF. You can open it, download it, whatever, and you can check everything. So you will learn everything about the AD converter and the library as well. So the specific library is made for Arduino-based microcontrollers, and they work with these microcontrollers. I will talk a bit more about this, how they work and so on later. So let's go to the table of contents. So you can see that there is a lot of things regarding the library. So I made several sections, and I have a little bit of introduction about the library and also about my custom circuit made for the ADS1256 AD converter. And then I talk about the AD converter itself a little bit. So I read the official data sheet from Texas Instruments regarding this board, or regarding this chip. And then I just collected most of the important things into a small section here in my document. But of course, if you want to know more details, you just read the original data sheet of this AD chip. But that is more technical, and here I try to, let's say, translate it to a bit more understandable text. Then the most important thing is the registers on the AD converter, because that's how we communicate with the AD converter. So I show you how to read and write the registers on the AD converter, and then I talk about the different registers which we can use to, for example, change the sampling speed or change the input pins, or have different kind of things inside the AD converter changed. And then I talk a lot about the coding, so how you can use the library, how you can reach different functions of the AD converter, for example, how you can modify the programmable gain amplifier, or how you can capture data continuously, how you can switch between the input channels either manually or automatically during the acquisition, and so on and so on. So that will be discussed in the coding part. And then I also tested the code just to check my work first of all, and I also wanted to check my circuit, which you will see very soon. So I summarized a little bit of this test, and finally there will be a section which will keep track of the changes. So both this document and also my library can potentially contain mistakes, because I did this totally alone, so no one was checking my work. Therefore, I might have overlooked some things. Therefore, if I get any kind of feedback regarding my library or regarding this document, then I will consider those suggestions or corrections, and then I will fix those and keep track of those changes in this document. And then this document will be always updated on the website, and then you will always see the most recent version of both the document and the software. So a little bit about the introduction. So ADS1256, we know that this is a 24-bit 8-channel AD converter. If you use one channel, you can go up to 30 kilohertz or 30,000 samples per second acquisition rate. Or if you want to switch between the 8 channels, then the maximum speed that you can reach is around 4.3 kilohertz. The AD converter itself communicates with the microcontroller via SPI, serial peripheral interface, and then whenever you choose your microcontroller, you have to make sure that you are aware of its SPI pins. And then on the AD converter there are some other pins like the data ready, chip select, sync and reset, which have to be determined by you, by the user. So you have to assign the pins for these connections on the microcontroller, and you have to control them. But this is taken care of in my library. And here you can see my custom board, and you can get this board assembled by me if you want. go to my website, you can contact me and we can discuss the details about this board. If you want this board and if you want to buy this from me, I will assemble one for you, test it and post it to you. Otherwise, you can go to the website of PCBWay. Link is also in the description and on my website. And you can buy just the PCB from them and you can assemble your own board, because I published everything, bill of materials, the schematics and everything. So you will be able to assemble this if you want to assemble it yourself. But there is a, let's say, third option. You can get this ADS1256 AD converter on an already made board. On AliExpress, for example, you can find a lot of these kind of boards. I put an affiliate link on my website. Please use it if you buy those boards, because then you can support me. And those boards are typically used with Arduino microcontrollers or these STM32 blue pill microcontrollers or even Teensy microcontrollers. I actually tested them with Arduino, Nano, Uno, Teensy as well, and two different kind of STM32 microcontrollers, and they work properly with my library. So hopefully it will work for you as well. So yeah, this library is not only made for my board. However, I developed the library using my board, but it works with any kind of Arduino-compatible microcontrollers. One more thing, that if you use my work for your own, let's say, publication or any kind of published material, please refer to my document. That's very important for me. So here is the, let's say, citation format, how you should refer to my document, and then you can just put it in the references and everything will be nice. And finally, if you want to support me, for example, to further develop this library or make similar things in the future, please consider becoming my Patreon. That helps me a lot. And yeah, it allows me to buy all this hardware and take my time, buy some pizza and develop the code. So then in the next section, I just talk a little bit about the AD converter. Of course, now I'm not going to explain it because you can read it yourself. That's why I made this document. But I just, as you can see, summarized most of the important things. One tip, which I want to give you in the beginning, that, for example, the original datasheet of this AD converter is always giving you the register values in binary format, like you see it here in the third column of this table. But when you communicate with the microcontroller and you communicate with the ADS1256 through the microcontroller, you will typically use decimal numbers. So just take your time and convert all these binary numbers into decimal numbers if you want to use your own, let's say, manual way of updating your registers on the AD converter. And then you can send these values to the registers instead of typing in all these binary numbers. It's much more easy to remember that number 99 belongs to the 50 samples per second acquisition rate than actually trying to remember what is 99 in binary or what is the binary number. So yeah, this is a good tip. And then this is how you can get the cycling throughput if you are switching between the inputs. So it's a much slower data rate. And then this is how you can calculate the bit based on this formula. So this is the LSB. And then the output code here can be seen in hexadecimal format on the positive and the negative range. And I put a side note here. I want to emphasize this again, that it's very important to precisely know the voltage reference value. So since you might be interested in millivolts or microvolts, your reference value should be also defined with millivolts or microvolts precision. Otherwise, you will get a slight discrepancy between the, let's say, real voltage or calibrated voltage and the measured voltage. So yeah, just make sure that use the precise Vref value if it's possible. So then I talk about the registers in the third chapter. So how to read the register, what is the code behind it, and what does the code do. And then I made some definitions for all the registers, so you can easily just type these names into the read register function parameter part, and then you will read the corresponding register. And I just named them according to their name, so it's very easy to take care of them. Then next part is writing the register. So again, I show you what each bytes do, how we write a register, what does the code do, and some examples. And here towards the bottom of the page, you can see that we can actually use numbers, and that's why I told you to convert the bytes, so the 8 bits, into decimal numbers instead of using the binary, because it's just much more easier to remember to them. But of course I have everything, like you can see it here. I have everything, let's say, named in the header file, so you don't have to necessarily convert everything, but if you want to use your own way of manipulating the registers, you can do it. And then status register, yeah, this is just important because you can enable or disable the input buffer, so you can significantly increase the input impedance of the AD converter, and that is very important for several circuits, because if you don't have that enabled, you can get a significant voltage drop, and you will have a huge offset in the red voltage and in the real voltage. So I will show you an example of this, because I specifically focused on this issue when I was testing the circuit and the code. And then the max register, this is the input multiplexer register. So this is the register which allows you to set or select the input pins. So here in this table, you can see what kind of binary value belongs to what kind of input, and you can mix these values based on the desired input channels, and then you can create a command byte, like I did it here down, and you can send this value or the corresponding decimal value to the register, and then those input channels will be selected. And here I did define all the possible single-ended input channels. That's very straightforward, because we have 8 pins, starting from A0, ending at A7. And the positive pin is always the A plus the number pin, and then the negative pin is the ground. So we measure between, let's say, 0 and plus 5 volts. That's the typical voltage range. But then we have the differential input channels, and the difference between these two channels is that for the differential input channels, both the negative and the positive input channels are on one of the positive input channels. So for example, instead of using the A0 plus ground, we use the A0 plus A1. And in this case, the input voltage can be not only plus 5 to 0, but plus 5 to minus 5 volts. So we can change the polarity. It will be, let's say, not sensitive to that, but of course differential measurement has further advantages. For example, less signal noise and so on. And I just defined the 4 possible combination of inputs in a sensible way, but of course you can select any kind of random combination, but I just combine the adjacent channels as differential input channels. And then AD-con register. Here I would not talk about the digital pins. You can use them, these CRK and SDCS parts. I think for average users it's not really useful and not really relevant. But the last 3 bits or first 3 bits, depending on from which direction you read, we have the PGA bits, and that is this table down here. So basically with the PGA bits you can set up the measurement range. So that is very important because with this you can maintain the resolution of the AD converter. So for example, if you know that your signal is always in between plus minus 0.5 volt, then you don't need to use the highest measurement range, but you can go down to the 0.625 plus minus 0.625 volts or 625 millivolts input range. So then that, let's say if I want to very simplify everything, then the 24-bit resolution is spread or distributed between this plus minus 0.625 watts instead of distributing the 24 bits between plus minus 5 watts. So yeah, you can see that the resolution is maintained. And then of course each of these functions are demonstrated here and introduced and explained, and there is always an example. And then we have the D rate register. Not too much explanation is needed because this is just you set up the sampling speed, and a very easy function is developed for this. So I have the set D rate function, and you just simply write in the corresponding sampling speed, and you cannot change it to any kind of random value. It has to be one of the defined values based on the data sheet of the AD converter, because how the data rate is used is that there is an input averaging or averaging, I don't know if mechanism is a good word, of course it's not a good word, but some kind of mechanism inside the AD converter chip, which by default always samples at 30,000 samples per second. But then if we turn on the averaging, then if we use, let's say, averaging of 2, then every second sample is kept. So we divide the original sampling frequency by 2, and then if the averaging goes up to 4, then we divide it by 4, so 7.5 kilohertz is used, and so on and so on. And that's how we go down in sampling rate. So we apply more and more averaging. But that happens behind the scenes. So all we have to just take care of that we set up one of these values. I/O register. Again, I would skip this, at least explaining it here in the video, because first of all, it's not really useful because we have a microcontroller which always have a bunch of I/O pins, and it's much more easy to manipulate those I/O pins on the microcontroller than reaching out to the AD converter and then getting an answer from the AD converter. It's much more efficient to work with the microcontroller. But if you decide to use the I/O register, then you can read all the different lines that I wrote here. You can read all the documentation, and yeah, it should work. And then the calibration. I would not go into details. Read the datasheet, both my datasheet and the original Texas Instruments datasheet. The most important thing is that whenever you do something with the AD converter, you reset it or something, run a self-calibration so that we make sure that an internal calibration is performed in the AD converter, and therefore you get good readings. And then about the coding, I would suggest you just to read this because it's a lot of text, so I'm not going to explain it here. But all we have to do is that we have a constructor, and therefore we have to define the, let's say, custom pins in this: data ready, reset, sync, chip select pins in this. Reset and sync can be optional, so they can be just written as 0, then the code will know that we defined it. And if they are 0, they have to be tied to the positive supply voltage by the user, if you don't use my circuit, but you use an external AD converter circuit. Plus, we have to tell the value of the voltage reference to this constructor. So it will know what kind of value to use in the formulas when it converts the 24-bit raw data into voltage values. And then how to create an instance, I will show it when I show you the code in the Arduino IDE. And then I also show you how to change the data rate and so on. And there is an initialization has to be done. You can see that I just manipulate the chip select pin, and then I take care of the reset and sync pins if they are relevant, if they are defined by the user. And then SPI is being turned on, so we can communicate with the AD converter. And then I just give some default values to the AD converter, so we can straight away start with the conversion after running this initialization function. Then before showing you the acquisition related functions, I show you how to convert the readings into voltage. So this is how it's done. We read in the raw data that is typically stored in a 32-bit variable. And then we check the 24th bit or 23rd, depending on how you look at it. If it's 1, we know that the number is negative, because the first or last bit, depending on, again, which direction you read it, is the sign bit. And if that sign bit is 0, it's a positive number. If that sign bit is 1, it's a negative number. If it's negative, we kind of mirror the readings around 0. And finally, we use the formula from the data sheet and calculate the output voltage based on the voltage reference, the raw 24-bit conversion value, and the selected PGA value. And then this function returns with a float type number. Then I show you how to read a single conversion. So this function really just reads one conversion from the AD converter, and that's all. So everything is shown here, how the code looks like inside the library and what does the code do, almost line by line explained here. And then how to read continuously. It's basically the same as the previous function, but here what happens is that we start the reading with a different command inside the AD converter, and then the reading goes on and on until we stop it. So this will be a bit different than just reading a single conversion. And then since this continuous reading has to be stopped, I also made a function which stops this continuous reading, and this is what is inside that function. And then I implemented two functions, one for the single-ended inputs and one for the differential inputs, to cycle through the input channels continuously. So what this function do, you can also read it in this document or in the library. It starts to communicate with the AD chip, it selects an input channel, and then it synchronizes with the AD chip and then reads a single conversion and sends it to the AD converter. And then it switches to the next channel, does a reading again, and send it to the microcontroller, and so on and so on. And after it reached the last channel, in this case it's the case 7, does a reading, and then it resets to 0 with this cycle variable. So it will return to the first channel, and then it will read over and over again until you stop it. And this is just some example how the output code should look like. So you can see it's nicely formatted. And then this is the same kind of strategy, multiplexing through the input channels, but this is for the differential inputs. And this is exactly the same as the previous function. The only difference is that here we select different channels in these cases, in this switch case part. And then about the testing. So first I tested the, let's say, precision of this thing. So I have this 6.5 digit multimeter. So I created, let's say, my internal reference, because this is not calibrated, of course. So I have my own voltage reference, an external voltage reference circuit based on the ADS1256 chip. And then I read its 2.5 volt output, both with this multimeter, and you can see the reading here on the photo, and also with my AD converter circuit. So I measured it with two different kind of settings. One was with the input buffer and what was without the input buffer. And here you can see the results and conclusions. So I did 100 readings and I averaged those readings. And what I got is that you can see it on the photo, but the output voltage was determined as 2.50116 volts. And with the AD converter, it was 2.49963 watts. So the difference in the readings was 1.53 millivolts. It's okay for me right now, so I'm not worried about this. But then when I measured this with without the input buffer, then measuring the exact same voltage, the voltage on the AD converter was determined as 2.09241 volts. So there is almost half a volt difference between the two readings. And then this reading is because there is a huge voltage drop caused, this 0.4 watts voltage drop caused because the input impedance was only 150 kilo ohms instead of the 80 mega ohms when the buffer is enabled. So this is very important. So this is, it's about nearly 500 times difference in resistance. So then we can imagine why we have this large voltage drop. And then I made a small code here. We have to tell how many samples we want to measure, and we measure that many samples, and we start the timer and stop the timer after the measurement is done. And based on the elapsed time and the number of samples taken, we can calculate the, let's say, real sampling speed. So we can compare these nominal data rates to our measured data rates. And I saw a small outlier here at the maximum sampling speed. I lost 200 samples for some reason, and I can see consistently that for some reason the 30 kilohertz sampling does not work well for me. So I will check this and fix this in the upcoming update. Then just some visualization of the nominal sampling speed and the measured sampling speed, so nothing spectacular here. And finally, the versions and the changelog. And this will be the first release. So then I just start this log, and then each new let's say version will have its own subsection here. And I will write down the details about the updates. So this is about the document, but once again, go to my website and check the document, download it, study it, and you will see how my library works. But I want to show you the code as well. So let's jump to the Arduino IDE and let's see how my circuit works and how my code works with my own library. So this is the source code which I include for my library, and this is now just let's say demonstration code, just to give you a starting point for using the ADS1256 with my library. But of course you can modify this if you find it if you find a better way to use my library. So I include the library, and then I have this constructor. So on my own custom PCB, these are the pins which I use for the corresponding pins on the AD converter. Plus now I was lazy, so I used 2.500 watts as the voltage reference. And then I made a few arrays here, and I just store the corresponding variables for the corresponding single-ended channels, differential channels, and so on. So it is easier for me to select a certain channel when I communicate with the microcontroller from my computer. And then I did the same with the PGA values, and then I did the same with the data rate and I did the same here with the registers. But here you can see that these are strings, so this will be just used when I print some kind of message on the serial terminal. But these are there, and there are some other let's say lines which take care of different variables. Here you can see that this will be the register number to be read by us, so that is also stored in a variable. But then this is the more important and interesting thing, is that we start the serial. If you have a microcontroller with native USB, this baud rate doesn't matter. If you use an Arduino Uno or Nano, it matters. So yeah, make sure that you use the proper baud rate. This is, for example, a proper value. And then I wait for the serial connection, and then I print some kind of message. So here I just keep track of the date of the latest version just for myself, so I don't mess up the code or don't mix up the code. And then after this is done, we have to initialize the ADC, and that's done. And then I assign some values to the PGA, to the MUX, and to the D-rate registers. And then after that is done, I read back those values. And why I do it is because I'm curious about the successful reading or writing, or both basically. So whether I was able to manipulate these registers. So then I just read the values back just to be sure. But then how to communicate is done here. So I just wrote a small introduction as a comment here, but what really happens is that in the loop, the microcontroller is constantly waiting for a character from the serial terminal, and based on that character, whatever we send to the microcontroller, there will be a function or a process started or stopped. So for example, if I send the small s to the microcontroller, then it will stop the conversion. If I send the capital L, then it will perform a self-calibration, as you can see it from this command. Or if I send capital G, then until we don't send the small s to stop the conversion, the microcontroller will constantly pull the AD converter and read a single channel continuously, and then print the values with 6 digits. And I did the same with cycling. So the large or capital C letter will cycle through the single-ended inputs, and then it will print the values. The capital D will do the same with the differential inputs. And then here is the speed test. You will see it, how it works very soon. And then I just made a test command. So if the Arduino is not frozen, it will be able to send back this println parameter. So whatever the message is written here will appear on the serial terminal. And then the small a will return a single conversion, so one single number with this message in front of it. And I made some extra functions to change the multiplexer, and this is where I want to use the arrays, which I set up in the beginning of the code. So here we select the input channel from the single-ended channels array. So I know, because I wrote it myself, that if I write 0, then that will select the A0 plus the ground as the input terminal on the AD converter. If I send 5, that will select the A4 as the input pin, and so on and so on. And then capital P takes care of the PGA value, F takes care of the sampling frequency, so the data rate basically. And then with the capital R we can read the registers, and with the capital W we can write the registers. And then here we have this registers array. This was with the strings. So then whenever I read a register, based on the number of the register, we will also fetch the name of the array from the name of the register from this array. So it will show up nicely in the serial terminal. So now it's time to do some demonstration. So I open the serial terminal. The AD converter is already attached to the computer. So I just find the port. Here we go. And then we can immediately see that the values are correct. Here you can see 0, 103, and 19. And first, I just really show you how this reading the register works. So it's this code. So let's read the first register. And then you can see that the value of the max register is 103. So we send the R that will start this case, and we send the number 1, which will be used in this serial.parseInt part. And then this R, or this number 1, will be passed inside this argument in the registers. So it will read the second value, not first, because first is the 0. So it will read the second value, which is, if we select it here, is the max, as you can see. So 1 is max, and if I read the R0, then it should be the status. If I read R4, for example, then that should be the D rate, or IO, sorry, 0, 1, 2, 3, 4. The D rate should be just 3. So it works. And now I show you the single reading. That should be the small a letter here. So I just type an A and press enter, and we get the conversion, as you can see. Always a little bit different, but up to the third digit, it seems to be stable. So then we can repeat this continuously with the G letter. You can see that it changes. Now it's a relatively slow data rate, but then this circuit now is connected to a potentiometer, so I start to turn it, so you can see that the reading is changing. Now I put it to 0, and then I go towards the maximum voltage. And that's all, basically. I have the buffer enabled, so I cannot go up to 5 volts. It stops at 3.7, but it works, as you can see. And if I send the small s and press enter, then it stops the conversion. So let's check the speed test now. So this speed test now is set up for capturing with 30,000 samples per second, and it has to convert 150,000 samples. So if everything is according to the nominal values, this should take around 5 seconds. So we will measure this time. So I just send a capital B and wait. Probably in 5 seconds we get these messages which are printed here. And now you can see this, I already mentioned that here we see that we captured 150k samples, and it took 5.16 seconds, or this much microseconds, sorry. And doing the math based on this, we have 29,054 samples per second as the real sampling rate instead of the 30,000 samples per second. So again, now as compared to my previous measurement, here I dropped almost 1,000 samples, and I still could not figure out why. So I have to solve this, but once I solve this, I will update my code and let you know the conclusions about this. And then let's see if I send a letter T, if this works. Yeah, it works. And yeah, the others are not really relevant. I can do anything here. Set up a different kind of frequency, let's say F3, and then I start the sampling, and you can see that it comes very fast. And actually, I show you something. So I close this terminal and open the serial plotter. And if I send this G again, there is our line. And you can see that now I'm in real time, I'm moving the potentiometer. And you can see that it nicely follows the things. And if I send the letter S, then it's stopped. Let's go back to the terminal. And it still works. So yeah, basically this is about the code. Feel free to check it. And to summarize everything, again, please check the link in the description. There is my website, and I made a dedicated page on my website for this library. So you will see all the resources there, my PDF. You can download the zip file, which contains the library files, plus this source code for the Arduino. And then you will see a link for PCBWay, where you can go to their website and order my custom-made board. You will see a link for contacting me, so you can buy the board from me. So I will assemble a board for you. I have the parts for several boards, so I can make it quite fast and ship it to you. And then there will be a affiliate link if you have already decided to buy the board from AliExpress, for example. You can buy them for a relatively reasonable price, and then you can use it with any kind of Arduinos or Arduino-based circuits. Then in that case, I just want to ask you to please use that affiliate link, so you help me with that. Or if you are really ambitious about supporting me, you can support me via Patreon, and that allows me then in the future to buy more hardware and pay for the website, for the hosting services and so on, and I can create more content based on this kind of circuits or microcontrollers or AD converters. So I hope that this video was useful to you. I hope that you will enjoy using my library and you will find it useful. If you find any kind of mistakes, or if you find any kind of silly things which I talked about or mentioned or made something wrong in the code, please let me know in the comments section, and I will fix it. So I hope you learned something, and see you in the next video.